In this video, we want to tell you about how we use colorimetry to study the concentration of solutions or to determine the concentration of unknown solutions. So colorimetry is probably what it sounds like. It's basically using a measurement, that's the metry part, to study the color of a solution. And by studying the color of a solution, we can figure out how much of a certain solute is in it, and we can estimate or calculate very specifically the molarity of the concentration, moles per liter, of a solute in a solution. So colorimetry is sort of explained in the next few slides, and we've shared these online for you in Google Classroom, and you should have access to them. So don't feel like you need to write all this down. Just kind of listen to a few of the high points as we go, and then keep in mind you'll have access to these notes in your Google Drive or in Google Classroom. So as you need them, you can access them whenever you run into need for it. So we can look at a solution of any color, and you see here a whole bunch of different solution colors. We can study yellow ones, red ones, blue ones, green ones, anything at all by shining a light through it and measuring how much of that particular color is being absorbed by the solution that's in the little container. And these little square containers that you see are called cuvettes. I'll be showing you a number of cuvettes throughout the video and showing you how we use these and some of the instruments that we use in order to make measurements. But we put a sample in there and then we shine light through it, and we can shine light of various colors through solutions of various colors. And by looking at how much light gets through and how much is absorbed, we can very, very specifically and mathematically estimate exactly how much of the solute that's giving it that color is present in the cuvette, in the sample. So colorimetry is measuring how intense the color is, and then using the data that we gather to draw a graph usually, and then use that graph to make estimations about things we haven't identified yet, looking at our unknowns, for example. So in colorimetry, what we need to do is choose a color that complements the solution's visible color. So the color that we choose, again, is kind of across the color wheel from what we're trying to analyze. So if we're trying to, for example, take an orange solution and analyze it, orange solutions look orange because the orange light is getting through them and coming to our eyes. So we wouldn't use orange light to study an orange solution, otherwise it just goes right through. To study an orange solution, we would use whatever color is opposite it. And you can see here on the second image in this picture that right across from orange is kind of a blue color, maybe a bluish green. And so the opposite color is the one we want to choose. Choose a wavelength of light that would be in that blue-green kind of range, and an orange solution will absorb it very effectively. A green solution, for example, transmits green color through quite well, but other colors are absorbed in various degrees, and we would choose then a color that's across the color wheel, complementary to green. Down here in our images again, if I look at the first picture, I see that green on the bottom here is complementary to red. And so I would shine a red light perhaps through a green solution to analyze just how green the solution is. And that seems a little funny, but we can measure how green or how intensely green a solution is and tell you how much of the green solute is in it. And I'll be showing you one of those here in just a minute. What we also can do is take a look at a sample in a device called a spectrophotometer. And what that does is measure the full spectrum, that's the spectral part, the full spectrum of light, that's the photo part, and the meter on that name is the measurement. So we're measuring the full spectrum of light, spectrophotometer. This is a spectrophotometer. Well, you can see that here. The spectrophotometer, this is a particular brand that we use, has a little spot where you stick the sample in here, and then it shines all the different wavelengths of color through it, and it measures which of those wavelengths of color is absorbed the best and which is absorbed the least. So on the screen here, you see what's sort of the output of a spectrophotometer. This is graphing all the different colors of the rainbow, from purples to blues, across to greens, yellows, oranges, reds. And then across the front of it, it plots a graph. And that graph shows us that in this example, the blues and purples on the left side of the diagram here, the graphic, are absorbed a whole lot. The spike is very high over here. But down toward the middle in the green-yellow range, there's not a lot of absorption happening. In other words, the green and yellow lights are going right through. And then on this end, the red light is probably going through quite well. And so in this case, or I'm sorry, the red is being absorbed slightly well. And so in this case, we may be able to make an estimation as to what color this solution probably is and which color this solution probably isn't. Down toward the end, this solution has a very, very low red absorption. So it's possible that this solution would be kind of a red in color, and the red is just coming all the way through, while most of the other colors are being absorbed fairly significantly on the graph. So it says here, let's try a few. Let's do that. So I'm going to switch out of this and take you to the SpectraViz. And that looks like this. So now you're looking at a graph or a blank screen anyway of what it looks like before we put a sample in. And this is in Logger Pro. So we've got the screen up to show us what sort of measurements we'll get from our SpectraViz. So I've hooked up the SpectraViz, as you saw before, to the computer. And right now it's not reading anything because there's nothing in the sample space, right? So what I'll do first is stick a distilled water sample in there. If I can find my distilled water sample. Here it is. Stick that in there. And distilled water, as you know, is very clear without any colors at all. And so it shouldn't absorb really any wavelengths of color significantly at all. You see here that the only ones being absorbed even a little bit are over here in the blue range. Okay? This particular sample is measuring just a tiny bit of absorption over there, not a whole bunch. So a pretty flat line. A solution without color will basically have a flat line. But if I take a solution that has some color, so I have here a blue solution, bright blue solution, you can see. And this is just a dye that we've put in there. But this could represent like copper sulfate or copper chloride or something like that that has a blue color. And we can tell how blue it is. And we can also show that blue light is not absorbed by a blue solution. Red light is, and other wavelengths will be. So I'm going to take this and I'm going to put it into the SpectraViz here and see what it tells us. It takes a few seconds for it to do its reading. And you see here that this has got a huge spike at like orange into red. And very, very low information or very low absorption over on the blue end of the spectrum. Now that makes sense. Remember, our complementary colors, let me back up here, our complementary colors for blue were orange across the color wheel on my slide here. And so blue should have high orange absorption, and sure enough, it does. So our data supports what we're saying. The color that's opposite is the one that's being absorbed. Let me switch that blue one out. I'm going to stick a red one in there. Take a look at that guy, get some red food coloring. Not a lot of solutions in lab that have that quite red color like common salts or anything. Maybe like a cobalt chloride would be kind of pinkish red, or maybe some iron stuff, but not a whole lot of this true red. Again, this is just a food coloring sort of dye. We can put it in there and we can see after a few seconds that red is not absorbed at all. Over here on the right side of the graph, it's basically zero red absorption. But over here in that green wavelength, man, the absorption is quite high. And so the green is being absorbed best by a red solution. And again, if we go back to our color wheel, the very first of our 6 combinations here shows that red is complementary to green. So a red solution will absorb green light, and we should be a green solution like this one, okay, which could be like a nickel sulfate or something, should absorb red light quite well. And if we put it in here, it's more kind of toward the orangish end of the spectrum of our red. But yeah, red and orange, kind of similar colors, are being absorbed fairly well. Now you might be surprised to notice on this graph that purple wavelengths are being absorbed fairly well. So we've got a green solution here that's composed of actually a little bit of blue and a little bit of yellow that we've put in there. And because of that, we maybe have a mixture of our dyes here. There's 2 different dyes that are sort of acting on that. The blue one is absorbing slightly in the orange wavelength here, and the yellow that we've put in is absorbing in the purple. So because there's 2 in there, we've actually sort of got double peaks here because we've got a mixture. A blue and a yellow are absorbing in the orange and the purple wavelengths respectively, while the blue and yellow dyes themselves that are in there are passing green light, or blue light rather, right on through, and we see that green peak is rather low. Okay, so as we look at that, we're going to use a spectrophotometer to pick which wavelengths are best. So I'm going to put a green one back in. We're going to study some green solutions. So you can see here, I'm going to figure out that along the way here, my data, I'm going to try to pick an orange wavelength, okay, in order to study a green solution. So if I come out here on my graph, I'm going to try to choose something that's in that green area, that green band on my data. If I put my cursor on the peak there, my wavelength there is in the area of about 630 nanometers. 630 is a wavelength then. And so when we do our measurements here, I'm going to choose a color that's in that 630 range because that's going to absorb the best from my green solution. And I'll show that to you here in just a second. Okay, so what we're going to do now is study our green solution, and I'm going to show you how we set this up. So you see here in the picture that we have several green solutions in our beakers. What we're going to study here is nickel sulfate. So we've got sort of a nickel sulfate solution mixed up here with green flask full of green, or a clear flask full of green solution, and we've mixed that up as a 0.4 molarity of our nickel sulfate. What we're going to do is kind of dilute that over the course of several samples and start with a dark concentrated sample and then water it down, if you will, or dilute it down. and keep track of those molarities as we do. So we start with a concentrated solution, take some of that out, add some water, and it's going to get diluted, and the green's going to fade and be less intense. Take some of that out, add some water, and it'll get less intense still. And so we can kind of have a series of samples, and we call that a serial dilution. We make them gradually lighter and lighter, and that means there should be less and less of the solute, in this case our nickel sulfate, present in the solution in our serial dilution. Okay? As we go, we're going to measure how much light is being absorbed by each solution along the way, and as we go, we should find that the fainter the green is, the less light is going to be absorbed, and we should see that the data shows up as pretty linear on our graph. We're going to look to collect some data. Okay, so let's jump over to our Logger Pro once again, and I've switched my device now. We had our spectrophotometer in there, and that was going to help us to check which wavelength was best. For our green sample, if you remember, the best choice was like an orangish red wavelength, and I said around 630 nanometers. Well, here's what we call a colorimeter, a very fancy name, but colorimeter. And a colorimeter has on it settings for various wavelengths. That's how well you can see these numbers, but right here is a row of several numbers that tells us we can choose different wavelengths, and the light is lit up over here, okay, next to 635 nanometers. We've got other choices along the way here, all the way down into the 400 range. And if you look along the bottom here, there's choices for blue light, purple, for some yellows in the middle, for some reds. And we've turned it over here to the red end of the spectrum. So we've chosen that wavelength as the one we're going to test. And so this colorimeter device is now set up and ready to use for red light. It's going to shine red light through whatever sample I put in. And what we do is we open this little gate, and you see there's an opening in there. We stick one of those square cuvettes in there. A red light will shine through it. And there's a sensor on the other side that will measure how much of the red light is getting through and how much is not. And that'll tell us that how much is being absorbed by the solution. So what I've got here is several green solutions that I've watered down. I'm just going to show them to you real quick. This is our original darkest stuff. Okay, that's my dark green solution. We're calling that about a 0.4 molar. Then I watered that down a bit to a 0.3 molar. So you can tell these side by side, they're pretty similar, but this is a little darker. This is a bit fainter. Okay, this is my 0.3. I've also got a 0.2, which is fainter still. And again, tougher to see on the computer, but this is my lighter one here. So this is a 0.2 molarity. Keep that one up here. And then a 0.1 molarity. It's half again as faint. So this is, or as dark. So this is my 0.1 molar. And then the last one I've got is a 0.04 molar. Quite faint, quite watered down. Now still quite a bit of green in there. But we've come a long way from the original 0.4 all the way down to the 0.04. Hopefully you can tell that that's a lot faded out. Still the same color of green, the same solute is in there, but a whole lot less of it. Okay? So what I'm going to do is I've taken a little sample of those and I've put them into my cuvettes. So I'm going to stick it into the colorimeter here and make measurements along the way of how much the absorbance is for each one. And on the screen here, you're going to see the data is going to be collected for each sample as we go. And we're going to enter it into our little data table. So if you're following along here, what I'd ask you to do is make a little data table like the one you see here on the left. Let me zoom in a bit for you on that. And hopefully you can see the headings here are concentration in moles per liter. That's molarity. We've got absorbance, which is the number we want to measure. And then you'll also see here is percent transmittance, which is telling me kind of the opposite of absorbance, like how much of it's getting through, how much of the light is transmitted through, up to 100%. Like in clear distilled water, 100% transmittance or very close to it. In a green solution, we're going to expect that not all of the orangish red light is going to get through. Some is going to be absorbed, some is transmitted. So we'll shine it through and see. We're going to start with our 0.4. So I don't know how well you can tell here. I'm trying to see how well my camera is appearing for you, make sure I'm showing it to you. So this is a 0.4 molarity of my nickel sulfate. I'm going to put that into my colorimeter first. Okay, I've stuck my 0.4 molar sample into my colorimeter and I close the door on the top, and the absorbance takes a little while to stabilize, but you see it's kind of stabilized here around 1.18 or so. Okay, I want to keep that data. Now that was my 0.4 molarity, so when I click keep, it kind of locks that absorbance at 1.190, and I'm going to tell the computer that was a 0.4 moles per liter sample. And when I do, it stores it up here in my corner screen. It says that was a 0.4 molar solution absorbance was 1.190, and the transmittance was only 6.46%. In other words, 6.46% of that orange light we're using got through. The other 93.5% was absorbed by my very green solution. I'm going to go to a lighter one. So this is my 0.3 molar, a 0.3 molar solution. We'll put that in there. And ideally, now we're expecting more light will get through because it's not as dark. Right? Now I'm going to let it stabilize again. I'm going to click keep again. And I'm going to say that was a 0.3 molar solution. And you'll notice it's stored that in my data table. I'm going to switch that one out and go to a 0.2 molar solution. So now we're down to half the original greenness, supposedly, of our starting one. Put that in my little colorimeter, close the gate. Let it stabilize. Click on keep. And I'm going to say that was a 0.2 molar solution. And again, hopefully you're making a data table of your own. Make a little data table that has room for concentration and absorbance for 5 samples is all you'll need. Okay. The next one we're going to use is a 0.1 molar concentration. Lighter and lighter. Close my gate on the colorimeter. Let it stabilize a bit. Click keep. Oh, that's a 0.1 moles per liter solution. Okay, and for our final solution, the lightest one, we had that 0.04 molar concentration. So this is going to be really pale. It's a 0.04 molar solution. Man, it's hardly any green in there at all. And again, I'm just going to show you side by side that compared to the original one that we started out with, really quite green. This last one's really, really faint. We can't see a lot of green, but the colorimeter can actually see a lot in that faint solution. So drop that one in our colorimeter next, close the gate, and you can see the absorbance is very low. We're going to keep that last data point and tell the computer that that's a 0.04 molar concentration. Now I've got 5 data points on here and we're good to go. Okay, we're good to move on and see if that data gives us kind of a trend and a pattern. So I'm going to click stop on here. And we're going to run some analysis on this. So what we actually do then is we take our 5 or however many data points you have. It could be fewer or more. 5 is a pretty good number. And we want to have a data curve or a best fit line to fit that. So I'm going to have my Logger Pro software give me a linear fit of my data. And you know, if you've taken some math and done some best fit lines, that we've got a best fit line that kind of goes through and sort of averages essentially all those points out and it crosses kind of right between the middle of them all and gives us a nice linear fit. And the next thing and kind of the last thing I want to do with the solution curve that we've set up here for our nickel sulfate is to analyze an unknown. And an unknown is another solution that we don't have a concentration for, but that we can put in and measure an absorbance for, and then use our best fit line to determine the concentration. So what I've got here is just another kind of random sample. This hasn't got a concentration on it. We don't know for sure what its molarity is. But I'm just going to put it into my colorimeter and let it take a reading. And you can see here it's reading live. I've got an absorbance of about 0.724 on the unknown solution that's in that cuvette. And so what I want to be able to do is go out here on the graph and find out what that absorbance corresponds to as far as the concentration. So I'm going to keep that number in mind at about 0.724, okay, and kind of lock that number away in my head. And I'm going to take this tool we've got here that we can slide along the graph and put anywhere we want to, and I'm going to put it at an absorbance of about 0.724. And I can look at my curve here and watch my cursor. I don't know if you noticed, but down near the origin of my graph, it's telling me my kind of position of my cursor. And it's telling me now that as I position my y-axis, I move this up and down, my y changes. So I'm going to put that at around 0.724. And then I also want to measure where that crosses over the graph. So I've got my cursor sitting there at an absorbance of 0.724. And I've got my concentration displayed next to it as the X in that ordered pair. And that concentration, as you can see there, is reading at 0.233. So the idea is that with the absorbance of 0.724, that would represent a solution whose concentration is 0.233 molarity, or 0.23. And that fits in among my other data points fairly well. So that's how we're going to use sort of a best fit line to measure an unknown. We go to that representative absorbance, go across till I intersect the curve or the best fit line, and then read down to the x-axis to see what molarity that represents. It's a little easier to do when we draw it out on paper, and we can work with it there and kind of position and get used to it, play with it a little bit But in this case, we're able to use sort of a digitally drawn in or a computer drawn best fit curve and do the same thing. So that's it for this video. All I wanted to do there is get you a little background on how we do colorimetry, sort of the basics of how we choose colors, and some of the devices that we use to make measurements along the way to help us get the data. In the next video, we're going to take some sample problems and work you through where you already have the data collected, how we set up the graph, how we draw on a best fit line, and then how we draw conclusions about unknowns using the best fit line that you've drawn. Thanks for listening. We'll see you then.